Electrolyzer Model Demo Session. Let's get started. This is a collaboration series with Aspen Tech. For more information, stay tuned until the end of this video. Welcome guys to this model presentation demo session. This time I'm with David Tremblay from Aspen Tech. He's the well-known guy for the PEM and all electrolyzer models. So David, I think the best person to introduce yourself is you.
Certainly. So I'm currently the Senior Director of Product Management, responsible for the process simulation business. So that's the Aspen Plus and HYSYS business. I'm a chemical engineer by training, and I've been with Aspen Tech just over 34 years. So I'm happy to talk to you today about hydrogen electrolysis and our investment to support sustainability.
My main question, David, will be, did you work before with electrolyzer model, or was something that it get started with the industry, or maybe your clients wanted to learn more about that and the solution was not there? How do you get started?
Yeah, certainly. Well, I'll talk about the company and then myself a little bit. So Aspen Tech got involved in this whole area about 20 years ago when fuel cells were a very strong interest to the automotive industry. So we all know, what actually happened is lithium battery storage became the preferred power supply. But 20 years ago, it wasn't clear. And a lot of companies like Toyota and Ford and so on, they had very active programs for fuel cell development. And we had a division in our company that was working on fuel cell modeling using Aspen Custom Modeler. So we developed some solutions. We had a fairly large group of customers that were consuming those solutions. It turns out hydrogen electrolysis is very, very similar to hydrogen fuel cells, just the direction of the reactions is going the other way. Now, with the focus on reducing the carbon footprint and with large investments going on in sustainability, we decided as a company to invest in this space. So about 5 years ago, we reached out to some of our external experts. We worked with a company called Anna Coolant Systems, who's an independent service provider for Aspen, and they helped us develop a set of first principle stack models for alkaline, PEM, and solid oxide type stacks. We then took those models as a basis and we built further on them, bringing in rigorous thermodynamics, increasing some of the rigor around the gas crossover, and we're continuing to evolve those stacks today. So over the last 5 years, I've personally been working in this area quite a bit, but our R&D team has several subject matter experts that have been investing their time, and now we're starting to do service projects in this area as a company. So we're quite engaged in the space.
Okay, I love to see all the things that as a user of Aspen HYSYS or Plus you don't see. You see the software, you don't see the persons or how a model or a unit operation is brought to life. And it's very interesting to see that in less than 5 years, you were able to get the electrolyzer model. I know we're going to be talking about later on, but can you let us know the challenges on the unit operation per se, or what you were thinking and that something may change on the way that you saw, okay, this is going to be mostly useful for our users?
So it's a process of continuous discovery. We start from academic papers. And one of the challenges with academic papers is they always make assumptions. And, what you learn in the real world is sometimes assumptions are valid and sometimes they're too simplified. Over time, we've been evolving these models. For example, we've added some features to make them easier to calibrate because in the real world, performance decays. We've been adding more mechanisms for gas crossover, because that's a very critical safety issue. We're looking at the dynamics of these systems in more detail to make our models more realistic.
Okay, well, I think the main idea of the demo session is, well, for those that may not be quite familiar with the electrolyzer model, to get to know it and not only know that it exists, but also what is the power of this unit operation. So very quickly, David, can you tell us what we're going to explore in the next demo session?
Sure. So we're going to show two cases. One is a steady state case inside Aspen Plus using a built-in model. With that built-in model, we have two options. We have a sort of a shortcut option where I can specify the efficiency and the power and so on, and it will do a mass and energy balance. But we're going to focus on the rating model. So that's a detailed model that's going to calculate everything based on chemistry and physics and equipment geometry transport phenomenon, and so on. And then we'll switch to a dynamic model. With the dynamic model, which is in Aspen Plus Dynamics, but also using custom models, we'll look at how that system might operate under intermittent power sources. So we have solar and wind power. It's going to change over the course of a day, and we can look at how that the stack responds dynamically. So, startup, shutdown, controllability, those are all very important considerations. So dynamic modeling could be quite important for customers developing their own green hydrogen technology.
So guys, if you're not quite familiar, we had 3 previous videos in which we talked about the importance of hydrogen production, the green energy revolution that's going on, and what are the different aspects of electrolysis, and more importantly, the theoretical aspects that we're going to be modeling right now. So we are quite familiar with it, but it's not the same to know all this theory. We gotta go and dive into that. So let's get started, David, with the demo session.
In Aspen Plus and HYSYS version 14, we now have an electrolysis stack model. In Aspen Plus, that's going to show up under the reactors model group. So you see all the way to the right, we have the electrolyzer. This electrolyzer model can represent alkaline or PEM type stacks. Now here I've already incorporated that into the flow sheet. This is alkaline electrolysis. So in the process, I'm bringing in a demineralized water feed. That's to make up for the water that's converted to hydrogen and oxygen. That's coming into a header. So it goes through a pump, it goes through a cooler that removes the heat that's lost in the stack. And then the flow is divided into the anode and the cathode. So it's feeding both sides of the stack.
This is 50-50, the separation here?
It's actually a little more efficient to weigh the flow towards one side, because of the stoichiometry of the reactions. That's one of the operating conditions that one may choose to optimize, because one of the things we've seen is the formation of bubbles inside the stack has an influence on the ohmic and activation voltages. So balancing that flow to minimize the void fraction on each side of the stack can help improve the overall efficiency.
Yeah, because right now I see it's almost 1.4 ratio between the left and the right hand side.
Yeah, that's right. So earlier we did some sensitivity studies and we adjusted to this ratio to get a better overall efficiency.
Okay.
So coming out of the stack, we have our oxygen-laden stream coming out of the anode and the hydrogen-laden stream coming out of the cathode. Of course, the circulating fluid is concentrated potassium hydroxide. In this model, we're assuming the oxygen is just vented out. The hydrogen, on the other hand, is going through a catalytic oxidation reaction to remove any residual oxygen, and then through a swing absorption unit to remove any residual moisture, and then downstream to compression and storage.
Okay, it seems pretty straightforward. One question, block 1, is it a normal separator or is it an actual unit modeling the separation?
So in this case, we're modeling that as a two-phase flash. In some processes, you might have more of a multi-stage separator to effect a better removal of the residual hydrogen. So sometimes there's an overhead condenser that recirculates back to the flash drum on each side.
Okay.
So in this process, any of the dissolved gases that are remaining in the liquid, they get recirculated back. And then that's one source of gas crossover. So that does lead to some introduction of oxygen into the anode. And one of the very important operating conditions in the stack is to avoid having more than about 2% hydrogen on the anode side because of the risk of a hydrogen explosion.
And my main guess is we are venting some oxygen to avoid accumulation, but also we want to try to recirculate the most oxygen to enrich the stream.
Yeah, so one of the effects we see is when we operate at high current density, the generation rate of oxygen overwhelms the diffusion rate across the stack, as well as the amount of hydrogen that gets recirculated back. So there's no real risk at high current densities. The challenges are low current density. So low current density, the rate of diffusion is almost constant, independent of the operating rate, but the rate of oxygen generation is proportional to current. So there is a lower limit to the current density, and that's related to this risk of having too much hydrogen in the oxygen.
And the current is fixed by the user in the stack unit?
Yeah, so let's look at the specifications in the stack unit. So we have two different options. We can model using a shortcut approach, which is doing a mass and energy balance based on some very simple specifications like the overall Faraday efficiency, or we have a rigorous sizing and rating type model. So if I go to the rigorous option, we can then specify the operating conditions. So in the current version, we can specify either the power or the current. Current divided by the face area of the stack is the current density. We can also specify either the heat duty. So I'm assuming an adiabatic system here, and I'm cooling it with an external heat exchanger. Or I can set the temperature, and not worry about modeling the heat transfer in that external heat exchanger. This also gives us the option to represent an array of systems. So in this particular process, even though I have one block representing the stacks, there are actually 8 physical stacks in the system. And that's a pretty common arrangement. Usually the scaling in this process is done by having more stacks in parallel. And then each stack is configured of multiple cells. So in this case, I'm assuming each stack has 230 cells. Those cells are in electrical series. They're in flow parallel. So the flow of liquid to the anode and cathode in each cell is assumed to be equal. And by the way, the second option there, if I had chosen shortcut, I can model either the stack by itself, or I can model the module. So the module has the downstream separators, the cooler, and so on. So when I model the system as the module, I can specify the gas purity directly. Okay, but in this case, I'm predicting the gas crossover and the gas purity, so that's that option is off. Now with the high fidelity sizing model, in this case, I can enter all of the geometry. So I've put in the cell area, the thickness of the channels that carry the fluid on each side, and a wide range of parameters related to the electrodes and the separator.
Most of this will be typically provided by the supplier of the equipment, right? But for people that is, let's say, the actual vendors of this equipment, are they going to be able to move individual cells and input to see which is the most optimal models? Or
our current model, we've put in reasonable defaults, and this is based on industry standard separators like Zirfon. So these are all based on what the vendor is claiming for their current set of separators. But these are open, right? This model is designed to be completely open because, again, this is a rapidly emerging technology. There's new separators, there's new electrodes that are coming on the market. So, the intent here is that as the technology evolves, the customer will be able to, keep up with it. So, for example, if someone comes out with a thinner membrane that's maybe got smaller pores, we can enter all those parameters here. Okay?
And David, I know that you have been working a lot with this sensitivity analysis, and maybe I'm getting ahead, but can you let us know very quickly what are the main effects? Let's say we are trying to optimize the PEM cell. What are the main effects of, let's say, electrode thickness, porosity, all those parameters, or the typical parameters that someone will be changing?
So, the properties of the separator are quite important. For example, the thinner the separator, the more diffusion you'll get across the separator. So you get more gas crossover. But at the same time, it reduces the electrical resistance of the separator. Just like any resistor, the shorter the length of the resistor, the less current is lost. So there's a trade-off there between the overall performance of the stack in terms of the amount of energy needed to make a given amount of hydrogen and the gas crossover. The companies that develop these separators, they're doing a lot of ongoing development to move towards thinner separators that have better gas resistance. So they're better able to reduce the diffusion of the gases. So we expect that, as this technology continues to advance, you'll see improving performance and less gas crossover as these new technologies evolve. And by the same token, as new types of electrodes get developed, the parameters of the electrode, like the charge transfer coefficient and the exchange current density, these are fundamental to the types of materials used in the electrode. The companies that are developing these electrodes are improving the performance of these electrodes by altering the material that they're made from. In some cases, the physical form of the electrode, so using nanoparticles, for example, to increase the surface area and the roughness. And just like any catalyst, the better the catalyst, the lower the activation energy, which in this case leads to lower activation voltage, lower overall energy requirement.
I like the idea of being able to adapt as we get different materials or different strengths. And my main question will be, if I were to change the material of the electrode, those two are the only ones that are mainly affected?
Yeah, those are the electrical performance of the electrode. It's mainly those two parameters. There's also a roughness factor here, but you can think of that like a calibration factor that you can fine tune, based on measured activation voltages. And then you can see similarly, we have several parameters for the membrane, including diffusivity of the oxygen and hydrogen that influences their gas crossover. And then there's some calibration factors. One of the issues with electrolysis is the performance of the stack degrades over time. So, and there's a number of reasons for that. One of them being you have a very corrosive environment with concentrated KOH. So there is some corrosion of the electrodes. There are some passivation layers that may form. So the net effect is over time, you'll see a higher voltage in the stack at the same current density. So to account for that, we have a voltage offset. So here's set to 0 because we're assuming a new clean stack, but we could tweak that parameter later to match what's actually observed in the field at any point in time. We have another factor that accounts for electrical losses. So some current will leak through the metal frame and the anode and cathode channels because you have an electrolyte in those channels that carries current. And lastly, we have a fouling resistance, and that influences the ohmic voltage. So with these calibration factors and with all of the exposed parameters for the electrode and so on, it's quite easy to take any measured performance curve. So in this for electrolysis stacks, they measure something called a voltammetry curve, which is the voltage as a function of current density. We can take that set of data, put it into Aspen Plus, and then use the data fit feature here to fine tune the model parameters to match that measured performance.
So you don't need to be changing manually. You just get your data, get the data feed, and see what are the output, and just select them.
Yeah, exactly. And that's the first thing we've been doing as we, implement projects together with customers is first we calibrate the model to match a pilot plant or, a small scale plant that's already operating. And then, customers are using this to scale up the equipment, to look at design trade-offs like I described with the membrane thickness and to see how the whole balance of plant behaves. So, one of the advantages we have with the simulator is we're not just modeling the stack by itself, we're modeling the entire system. So earlier you asked about sensitivity studies. So here I've carried out a simple sensitivity study where I'm varying the current. So varying the current means the current density is changing. Looking at a number of the predictions of the stack, including the cell voltage, and there's several components to that cell voltage. The reversible voltage is from thermodynamics. The activation voltage is depending on the electrodes. The ohmic voltage is electrical resistance. We calculate the overall power that's consumed. And ultimately, we get some metrics that are related to the amount of power to produce a given amount of hydrogen. So if I was to, quickly look at some of those, let me look at the current density as the x-axis, and then we'll put some of these different voltages up. So I'm going to put them all on the same axis so we can compare. So, what you'll see, the blue curve at the top, that's the overall voltage across the cell. Of course, with 230 cells in the stack voltage would be 230 times that. You can see at low current density, this curve starts to slope downward. It would eventually meet this reversible voltage, the green line, if I went to 0 current density. The red line here is the activation voltage. That's related to the properties of the electrodes. So there's some energy required to get the electrons to jump off the electrode into the fluid, just like an activation energy in a chemical reaction. And then the purple curve here at the bottom is the ohmic loss. So that's the electrical resistance. You can see that's proportional to current. So it's a straight line. So when you add up these three terms, plus there's another concentration over potential that's quite small, you end up with the cell potential.
So the main thing that you will see that changes the most with respect to the input will be the red line or the ohmic resistance.
So, everything's changing and the proportion is not that different. If you look at the delta from the left side all the way across, the contribution of the activation voltage and the ohmic voltage are pretty similar. Okay, the concentration voltage is very small until you get to very high current density. Then it will turn up quite quickly.
It was exponential or?
Yeah, it almost goes exponential, and there is a limiting upper current because of that.
And the limiting concentration of oxygen has something to do here, the minimum value that we stated?
Well, let me come back to that. So there is some influence of the oxygen crossover. I didn't show that here, but I'll show that in a second in the dynamic model. Okay, but one thing we can see if we look at the current density and the specific power to generate hydrogen. Here, the x-axis is in current density, the y-axis is specific current in watts per cubic meter. We'll see at very low production rates, the specific power requirement's quite low. But as I increase the current density, I'm actually requiring more power to generate the incremental amount of hydrogen. So there is a trade-off here. Obviously, I want to run my equipment to its maximum capacity, but as I do that, I'm lowering the efficiency.
Yeah, and cost of energy as well.
right? And in this case, typical state-of-the-art stacks these days are at full capacity, they're running around 4.4 in that specific energy metric. So that's the steady state model. Now there's a lot of things that happen, dynamically that might also be interesting. So I'm just going to pull another case over here. This is an Aspen Dynamics case, and inside this Aspen Dynamics model, I have an open equation form of that same stack model, and I've also attached to that a wind farm model. So I'm modeling an array of wind turbines and a solar array model. And for the demonstration purpose, I'm assuming that I'm taking some power off the grid to ensure I stay near my minimum operating range. But as the day progresses, I'm assuming the wind is increasing. So I put a wind model in here that includes some noise and some steady increase in the wind. And I've also put in a schedule here for how the sunlight varies over time.
Mm-hmm.
In this case, in the morning, obviously there's very low solar intensity. And then as the day progresses, I have quite a bit more. Okay, so I'm just putting some forms here so that we can do a quick dynamic run. So I've just started the dynamics. Up on the upper left, I'm showing the solar energy. Towards the center, I have the hydrogen and oxygen. So that's that safety factor that controls the risk of an explosion. On the upper right, I have the hydrogen production rate. On the lower left, I have the wind power. And on the lower right, I have the current going through the stack. That's the blue curve. The green curve is the power. And then I also have the hydrogen production rate here. So what we're seeing is as the wind is increasing, my wind turbine is generating more energy. My solar array is also generating more energy. And that made the hydrogen production rate go up. Now, right here around 1.5 hours, the nature of these wind turbines is they have a transmission just like a car. And when the wind exceeded a certain rate, it changed gears, and that allowed it to produce energy more efficiently. But that also caused a disruption. So during that transition, it's temporarily not supplying power. And we'll see that impacted the stack. So we got a bunch of noise here in the stack. And, we can also see towards the upper center that around that time, we got fairly close to our safety limit for the hydrogen and oxygen. Now, as we continue to increase the current density, the hydrogen came back down. So we're back in the safe zone.
Mm-hmm.
Okay, so this is just showing how one might apply a model like this for using intermittent power sources like green energy. But another very important consideration is startup. When you first start these plants up, there's a tendency for the hydrogen and oxygen to shoot upwards. And typically that's countered by starting the plant under nitrogen blanket. So in the beginning, you'll be feeding nitrogen into the two separators to dilute any hydrogen and oxygen that's present. As you start up the power and the system starts to generate oxygen and hydrogen, you can back away on that nitrogen. Now, obviously, nitrogen's expensive. During that period, you're also not using the hydrogen you produce. So there's a bit of an optimization problem between wasting product and maintaining safety. So using the dynamic model to come up with the best startup procedures can be quite useful for optimizing the overall performance of the plant. Okay, we can also, of course, look at the safety systems, the control system in much more detail in this dynamic environment.
You mean all the evolving system control systems?
Here I've got a very, very simple control logic, just regulatory control. But generally in the real world, there's some kind of master control based on the production rate. And everything else will be slaved off of that, like the water makeup rates and the various controls that influence the circulation rate and so on. So, but I think this is one of the main areas of focus for the companies that are licensing this technologies to develop appropriate control strategies, ways to deal with power intermittency and so on. The other thing I'll add is here in the dynamic environment, because I have access to custom modeling, I could also add more detail to this model. So this is an open equation form, and we have had customers modify this to represent special types of equipment and modifications that they've made. We can also model things like the electrical transformer, the inverters and so on, which might be responsible for some electrical losses, right? So when you look at the overall system performance, you need to look at performance of the stack, but also the balance of plant, which includes things like the pump, the cooler, and those electrical circuits that might be resulting in some losses.
Do you get this with all these models were done by you, but if I am a normal Aspen user, can I find these templates or similar templates?
So with Aspen Plus and HYSYS, we deliver the steady state model, like the one I was showing.
Mm.
In fact, that was one of our delivered examples. We deliver examples for both alkaline and PEM. The PEM was added in a 14.1 update. So if you didn't update when we shipped that, it's about a year ago now, go ahead and look into that because it's worth getting the update to have that feature. The custom model, this dynamic model, we do have some open custom models that are published. This is a bit of a newer version. We do use this ACM environment to do our own internal development and research. So, customers that are interested in getting the most up-to-date stack model can talk to me, and we'll make arrangements to share that. Just my name, david.tremblay at aspentech.com. So you can see now, over time, as I've increased the current density going to the stack, my hydrogen and oxygen has dropped down to very low levels. And that's more of the typical operating condition that you see there.
And well, I think it's going to take longer, but how does these models when the night comes?
So I model like this, of course, I can program to do multiple days or multi-period or whatever. But in this case, I've set up the simulation to go over 12 hours. And eventually as the solar intensity decreases in the second half of the afternoon, this curve will come back down, and we'll see the overall production rate go down.
I can even picture that. Also, this is separated to the model, but I imagine there's a lot of like weather modeling for the wind and solar, clouds, rainy days, and all that. But that's a separate model.
Right. So as you get into that kind of phenomenon, we do have another solution for modeling stochastic phenomenon like weather, seasonality. So we have a tool called Aspen Fidelis. It's a Monte Carlo simulator. So in a Monte Carlo simulator, you can program in the types of events, including stochastic events like weather, which are subject to probability. There might be a known seasonality. We know that the days are longer in the summer than in the winter, but we don't know if a given day is going to be cloudy or not cloudy, right? So there's some predictable phenomenon, some unpredictable phenomenon. Those can all be described statistically. And then what the Fidelis system will do is it will model a system like this hydrogen production, or even a full value chain, producing green hydrogen, hydrogen storage, producing ammonia or methanol, the storage of those chemicals, transport, everything around the value chain. You're simulating at a lower level of detail. So, it's more like a mass and energy balance based on current conditions. But then you simulate that over many life cycles. So, you might represent, say, 10,000 life cycles of the plant, considering all this random phenomenon that can occur. And at the end, what the Fidelis will tell you is what's the expected overall capacity over a long period of time, given your current topology and the expected performance of the equipment. It will tell you which bad actors you have. So what parts of the system are the biggest source of loss of capacity. So for example, it might be pump failures. So if I lose this circulation pump, I'd have to shut down, right? And when I shut down, then there's some period of time that's required to fix that pump. I could improve that performance by having 2 pumps in parallel. So I have a standby. I could have 3 pumps in parallel, each able to handle 50% of the capacity. So there's many different scenarios that would influence the capital cost and the expected uptime. So between this set of tools, between process simulation, which will give you the mass and energy balance, that's an important input into the Fidelis model, which tells you how things behave stochastically, and cost estimation, which tells you the capital cost. Obviously, if I have 3 pumps in parallel, that's more expensive than a single pump. I can look at all the design trade-offs. Look at things like how much intermediate storage should I have? Should I be storing electricity in a lithium-ion battery, or should I be storing hydrogen in a pressure vessel, right? So there's many decisions like that have to get made as companies are developing value chains that leverage green hydrogen as part of the chemical production.
Those questions are very interesting for the present engineer that right now they need to take those decisions on whether to keep the hydrogen or to store the energy in batteries. That's something that I'm pretty sure is going to be very common to see in this type of industry.
In fact, there are some kinds of stacks that can act as batteries. So when they're not generating hydrogen, they can be accumulating power. So there's lots of technologies like that are emerging and are quite interesting.
But these are like novel, or you mean the ones that we're modeling right now, like the alkaline and the PEM?
So these are novel systems. So I mentioned earlier, some of our customers have
Okay.
developed custom stack models for new technologies. So that's one of the areas that our customers are looking at.
Okay. And I want to know a little bit more on the economics or financial things that we could be doing right now without the Fidelis software.
Mhm.
Can we already make some estimations on power costs, maybe product price that we are accounting for?
Yeah, so in Aspen Plus itself, we can use the utility feature. So through process utility feature, I can identify, for example, that I have cooling water, that cooling water costs a certain amount, per gallon or per equivalent cooling capacity. I have electrical power. So one of the things we added in addition to this electrolyzer stack, there's a new power stream. So I could have specified power here as a stream. That can be assigned to an electrical utility. Electricity has a cost. So Aspen Plus will calculate all the operating costs. If I, take the extra step of specifying those utilities, like the pump is drawing power, the cooler here is drawing cooling water, my stack is drawing power. This model can then be sent to our economics solutions like Aspen Capital Cost Estimator, or I could use the economics features here inside Aspen Plus, which runs the economic analyzer under the hood. And that will tell you also the capital cost of the system.
That
Okay.
that power stream is new for version 14, or it
Yeah, that
existed?
power stream is a new feature in both Aspen Plus and ISIS.
It's great to have now that be able to directly input that. I think
Right.
before you had to go directly into the unit or a utility stream. How did before were all those calculations on power calculated?
Yeah, so in the past, we didn't differentiate an energy stream, whether it was heat or power. So you could have attached a heat stream, for example, to a pump, and then you could assign the heat stream to electricity. But we've added this power stream because as chemical companies go through this energy transition, there is increased use of electricity to drive the plant, right? We even see now electrical crackers, coming online.
Yeah, I've seen a lot of news on that, on going electrical. Can you open the stream just to see like the novelty? Because I've never seen that.
Sure.
What exactly can you input the like direct current and AC, or how does it works?
Yeah, right now it's very simple. So we
Oh.
can enter power. So it's just on kilowatts. And of course, with direct current, if we know the power and we know the voltage difference, you've got the current or vice versa. Yeah. So in this case, I added a power stream. You notice the models may be incomplete now. That's because it's overspecified. So I would have to go in here
Set
and
up
go into
the
the stack and remove the power spec. So actually it did it automatically. So you see those are disabled now because I attached the power, but I
okay.
didn't specify the power, so it's still incomplete. Right, so if I specify that, now the system's complete. Yeah, we also see applications down the road if we wanted to compare, for example, an electrically energized compressor versus a compressor working from a steam turbine, right? We're just trying to make the simulation represent reality more accurately.
Yeah, for sure. Not always is going to be alternative or green energies, some fossil fuels or some furnaces, biogas maybe.
Right.
It's kind of useful for those willing to work with electrolyzers. And I really love the dynamic simulation, didn't expect that. And well, there's a lot of things that can be added on the things that are already existing on the unit operation. So I don't know if you want to add something else, David.
No, just thank you for taking the time to go through this with me today, and we're happy to help our customers get more involved in this whole area.
Looking forward, it looks awesome to see that Aspen is going to help all these process engineers willing to work with this unit operation that may be novel for some. It's the industry coming through. I really love, as a process engineer, maybe a junior engineer working with this type of units. You have it in the lab, but you can also go and model and simulate. I think it's great.
Yeah, and it's obviously important for the future as well, that we're moving more towards green energy.
Yeah, a lot of green hydrogen. Looking forward for that.
All right, thank you.
And actually, guys, this was supposed to be the last video in the series, but David got the great idea of having an extra video for Q&A. Let it be all the questions, doubts, comments that you may have regarding electrolysis and, more importantly, the electrolyzer model. So do not hesitate in ask any question in the comment section below. And of course, it may be very technical, it may cover very detailed descriptions, or it may be a very broad or generic question. Make no worries, we're going to be making our best to answer your questions. On our behalf, we will be waiting, and once again, thank you for joining us.